Episode 97, titled Decision Trees, Splits, Depth, Pruning, and Interpretability Trade-offs, we focus on a model family that many professionals appreciate because it can speak in rules rather than in opaque scores. Decision trees can produce explainable logic, capture nonlinear boundaries, and represent interactions without you having to handcraft cross-terms. That combination makes them attractive in governance-heavy environments, where stakeholders want to see why a decision happened and auditors want a defensible policy story. At the same time, trees can overfit quickly, and an impressive tree on training data can be little more than a memorization device if you let it grow without restraint. The decision points are therefore not just about whether you use a tree, but about how you control its complexity through depth and pruning. This episode builds the practical intuition you need to choose those controls and explain the resulting model honestly. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A split is the basic building block of a decision tree, and it is essentially a rule that divides data into two or more subsets based on a feature condition. For a numeric feature, a split is often a threshold such that values less than or equal to the threshold go one way, and values greater than the threshold go another way. For categorical features, a split often separates one group of categories from the rest, forming a rule that captures meaningful differences in outcomes. Each split is chosen to make the resulting subsets more pure, meaning the target labels within each child node become more homogeneous than they were before the split. When you follow splits from the root down to a leaf, you are applying a sequence of rules that narrows the population to a subset with similar outcomes. That path is what gives trees their rule-based interpretability, because the model can be read as a chain of conditions leading to a prediction. Understanding splits as rules helps you see both the power and the limitations of trees, since every decision is made by asking one question at a time. Split selection during training is driven by impurity reduction, which means the tree chooses splits that most improve the purity of the child nodes relative to the parent node. Impurity is a measure of how mixed the labels are in a node, and a good split is one that separates classes or target values so the children are more consistent. The training algorithm evaluates candidate splits and selects the one that yields the largest reduction in impurity, effectively choosing the split that best separates outcomes at that point in the tree. This is a greedy process, meaning it makes the best local choice at each step rather than searching for the globally optimal tree. Greedy splitting is one reason trees are fast and intuitive, but it is also why they can be unstable, because a small change in data can change which split looks best early on. The practical implication is that impurity reduction explains how trees decide, but it does not guarantee that every chosen split reflects a stable, meaningful relationship. Depth is a primary control on tree complexity, and it directly governs the trade-off between fit and generalization. As depth increases, the tree can represent more detailed rules, carving the feature space into smaller regions and fitting training data more closely. This often improves training performance because the tree can keep splitting until each leaf contains very few mixed cases, sometimes reaching near perfect fit. The risk is that deeper trees can model noise as if it were signal, creating rules that are too specific to the training sample. Overfitting in trees often looks like very confident predictions based on narrow conditions that do not repeat reliably in new data. Depth, therefore, increases expressive power, but it also increases the chance that the model is learning quirks rather than general structure. The exam expects you to connect depth with overfitting risk, especially when data sets are small or noisy. Pruning is the set of techniques used to simplify a tree so it generalizes better and remains more stable, often by removing branches that add little predictive value. Conceptually, pruning asks whether a complex subtree provides a meaningful improvement over a simpler decision at the parent node when evaluated on data not used to build that subtree. When pruning removes a branch, it replaces it with a leaf or a simpler structure, reducing depth and reducing the number of rules a prediction must traverse. This simplification can reduce variance and improve performance on unseen data, even if it slightly reduces training accuracy. Pruning is therefore a way to balance interpretability and generalization, because a pruned tree is easier to explain and less likely to memorize noise. The key is that pruning should be guided by evidence, such as validation performance or complexity penalties, not by aesthetic preference alone. Categorical splits require special care because categories do not have a meaningful numeric order unless the domain explicitly defines one. Treating categories as if they can be sorted numerically can create artificial patterns, where the tree splits on a numeric code that has no relationship to the outcome. The correct approach is to consider groupings of categories, meaning the split separates a subset of categories from the others based on how they relate to the target. This grouping can be learned by the algorithm or guided by domain knowledge, but the important point is that the grouping is about outcome behavior, not about an arbitrary label number. In practice, categorical handling also interacts with data sparsity, because rare categories can lead to brittle splits that do not generalize. A disciplined approach is to ensure that categories have sufficient support and to consider consolidating rare categories into broader groups when appropriate. This prevents trees from creating rules that depend on one-off categories and improves stability. One of the strongest advantages of decision trees is that you can explain a prediction path as a sequence of if-then rules that stakeholders can follow. A path explanation starts at the root and states the condition at each split, such as whether a feature is above or below a threshold, or whether a category belongs to a certain group. As you move down the path, you narrow the set of cases until you reach a leaf, which contains the model's prediction and often the distribution of outcomes observed in training for that leaf. This style of explanation aligns naturally with how many decision-makers think because it resembles policy logic and checklist reasoning. It also supports auditing because you can show exactly which conditions triggered a particular prediction. The discipline is to keep the tree shallow enough that the path remains comprehensible, because a path with too many conditions becomes hard to communicate and easy to misinterpret. Trees are particularly prone to memorizing noise when datasets are small, because the greedy splitting process can latch onto accidental correlations that appear strong in a limited sample. When a dataset is small, impurity reductions can be driven by chance arrangements of a few cases, and deeper splits can isolate those cases into leaves that look pure but are not representative. This is why unconstrained trees can achieve near-perfect training accuracy and still perform poorly out of sample. The warning sign is a tree that has many leaves with very few observations, each representing a narrow rule that feels too specific. Avoiding this requires controlling depth, enforcing minimum samples per leaf, and using pruning to remove branches that do not hold up on validation. The exam wants you to recognize that trees can overfit easily, especially under scarcity, and that interpretability does not automatically imply reliability. Comparing a tree's performance to baselines is a practical check that the added complexity and interpretability are delivering real value. A baseline might be a simple linear model, a simple probabilistic model, or even a trivial predictor depending on the context. And the point is to ensure the tree is not merely producing a compelling story without meaningful improvement. Trees can be attractive because they produce human-readable rules, but rules that do not improve decisions are still not useful. Baseline comparison also protects you from overfitting, because a tree that beats training metrics but fails to improve out-of-sample performance relative to a simpler baseline is likely learning noise. This discipline aligns with responsible model selection because it demands evidence that complexity is justified. If the tree does not outperform a baseline under fair evaluation, the safest choice is often to keep the baseline or to rethink the feature set. Trees naturally handle interactions because a split on one feature followed by a split on another feature creates a conditional relationship without explicitly adding cross-terms. For example, the tree can represent that a feature matters only when another feature is above a certain threshold by placing the relevant split deeper in the branch where that condition holds. This is one reason trees are good at capturing nonlinear behavior, because they can create different local rules in different regions of the feature space. Interactions that would require explicit feature engineering in linear models can emerge automatically in trees through hierarchical splitting. The trade-off is that these interaction rules can be unstable if data is limited, because the model is learning conditional patterns that require sufficient examples in each branch. When the interaction is real and supported by data, trees can capture it elegantly. When it is not, trees can create complex conditional stories that do not replicate out of sample. Instability is a known issue with decision trees because small changes in the training data can produce different split choices near the top of the tree, which then cascade into different overall structures. This is partly due to greedy split selection and partly due to the fact that multiple splits can appear nearly tied in impurity reduction, so small data differences change which one wins. Instability matters for governance because it can cause model behavior to shift unexpectedly between retrains, even when overall performance metrics remain similar. It also matters for explanation because stakeholders may see different rules and assume the model is inconsistent, even when the underlying predictive signal is stable. Controlling instability often involves limiting depth, pruning, and ensuring sufficient data per split so that split decisions are supported by more than a few cases. Recognizing instability as a risk helps you plan how to manage it rather than being surprised later. When accuracy matters more than single tree interpretability, ensembles are often the next step because they reduce variance and improve performance while sacrificing some of the simple rule clarity. Ensembles combine multiple trees so that individual tree quirks average out, producing more stable predictions and often better generalization. This is especially useful when a single tree is unstable or when the decision boundary is complex, because multiple trees can represent a richer set of patterns without relying on any one brittle structure. The trade-off is that explaining an ensemble is harder because you no longer have one clear path of if-then rules to show for a prediction. In many real deployments, teams choose ensembles for performance and then use separate explanation methods to provide governance insight, acknowledging that the explanation is no longer the tree itself. The exam-level point is simply that ensembles are used when you need higher accuracy and can accept reduced direct interpretability. The anchor memory for episode 97 is that shallow trees explain, deep trees fit, and pruning balances. Shallow trees produce short rule paths that stakeholders can follow and that are easier to audit. Deep trees can fit complex patterns and achieve high training accuracy, but they are more likely to overfit and less likely to remain stable across retraining. Pruning provides the balancing mechanism by cutting back complexity to what is supported by evidence, improving generalization, and often improving interpretability at the same time. This anchor captures the central trade-off you must manage whenever you use decision trees. If you remember this, you will naturally ask how deep the tree should be and how it will be pruned, rather than assuming the default tree is appropriate. To conclude episode 97, titled Decision Trees, Splits, Depth, Pruning, and Interpretability Trade-offs, choose a depth policy for one scenario and justify it in terms of stability and actionability. Consider a security triage model intended to produce rules that analysts can follow quickly during incident review, where false positives create workload and explanations must be audit-friendly. A shallow tree policy is justified because the rules must remain comprehensible, and a shallow structure reduces overfitting risk and instability across retrains. You would support this with pruning to remove branches that do not improve validation performance, ensuring the final tree reflects stable patterns rather than training noise. If the environment later demands higher detection accuracy and the cost of reduced interpretability is acceptable, you could shift toward ensembles. But for a rule-driven triage tool, a shallow pruned tree is the safer choice. The depth policy fits because it aligns model complexity with stakeholder needs and the reality that small datasets and noisy signals can make deep trees fragile. When you justify depth this way, you demonstrate a disciplined understanding of the trade-off rather than a preference for complexity. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.